All right. So now time for some general tips. So we've touched on a lot of different topics. We've covered a lot of ground on different specifications. Goal is to have everyone come away a little better informed in terms of which specs may matter or where to zoom in. So going back to capacity, it's one that is the start of the discussion. Customers generally may think they've got the capacity figured out, but the reality is it has a pretty important influence on the quality measurement or the life of the product, right? Is this thing going to survive or not? So really want to make sure that it's properly sized to give you as much signal as you can, but that doesn't have any physical damage. And we actually have composite loading calculations that we can run through if you have a scenario for an LP where it may have a lot of extraneous loads, you can't get rid of it, so we can work through that. And obviously we spec out, as you saw earlier, what our low profile product families can tolerate, and not only tolerate, but also the max error there. Other thing to keep in mind too is what is fatigue rated. A lot of times, a couple 100,000 might be thought to be fatigue rated. In reality, no, that's fine. You can use a standard load cell. Or if you do have a fatigue test, where you are going to be doing millions of cycles, and the load cell isn't fatigue rated, you can often just go up in capacity, or at least choose the right capacity to where you're going to be operating in a realm where the sensor can easily tolerate the cycle count. Especially keep in mind too if it's single mode. So our fatigue rated load cells, as you heard from Jeff, 100 million fully reversed cycles, right? That's both directions. When you're not cycling and you're not doing cyclic loading, that also greatly reduces the chance of any fatigue risks. So if you're doing just compression only or just tension only cycle, you're likely going to be fine with a non-fatigue rated, especially if you're only operating at, say, 30–50% of that load cell's capacity. So these are kind of good discussions to have with the AEs, the application engineers, to figure out exactly how much capacity you need. The other thing to pay attention to is just because you may find another load cell somewhere else, or you may be looking at two, pay close attention to what the signal output is. It is commonplace for some people. We don't do it very often, only I think on a couple products where we'll offer a half calibrated load cell as a specific capacity. Most of the time we try to maintain the same output across all stated capacities. So again, you may be thinking you're finding a load cell that's rated for half the capacity, meaning you're going to have better signal or better measurement, but in reality, you're just getting half the output. So pay close attention to the outputs when you're comparing capacities. All right, next one. So accuracy. We had a lot of specifications that are under that accuracy header. It's really difficult to just assign a certain number, but really it comes down to understanding how in your particular application, which specifications will apply, right? Which ones can you remove, which ones factor in, which don't. It's going to come down to the temperature profile of the test. If it's constant temperature, good. You can move all the temperature stuff off the table. It also comes down to your load profile. Like you heard earlier, if you're only doing a single ascending test, hysteresis, for example, doesn't matter. What calibration data do you have? If you have either your specific load point or if you have the curve data, then you can take out maybe non-linearity, even hysteresis again from impacting your measurement. So load cells are ratiometric. We mentioned this earlier. Pay close attention to the quality of the excitation that's going to that sensor, because any noise that's coming in on that excitation side is going to now show up in your measurement signal. So pay close attention to that. And again, in summary, sensor is just one line. So we spend a lot of time about sensor specs. That's zooming in on the sensor. Now you got to look at everything else attached to it. Next one. Temperature. We've touched on this a few times. Come back again. Key takeaways there to understand how it affects both zero and span. It's characterizable. You can probably compensate some of that out of your test or remove some of it. We can customize it. We want to make sure any temperature is as homogeneous or consistent as possible around that sensor. And then again, think about the rest of your system. If you can run your whole system up to temperature to see how it responds with no force, that would be ideal. Every single mechanical thread, any mechanical joint, that's going to respond differently to temperature. So even if you zoom in too much on the sensor, you may have other air influence that makes the sensor irrelevant almost. Next one. Calibration. So we could do a whole nother webinar on calibration, but for best performance and best match, you want to try to ensure your calibration is as close to what your actual test is going to be. So do you have tension or compression data? Do you need both? Do you only need one? Like we talked about several times, can you run a multi-point cal instead of just a single full-scale value? And then that's true for the sensor. If you're looking at the sensor specs, what kind of cal does it come with, right? Do you have a multi-point? Do you have a single point? And then the last part too, is it actually, what is the uncertainty of the calibration? So that's usually a separate question you need to have. You can be looking at two data sheets side by side, but if one's got a 0.04% or 0.02%, if it's a dead weight type cal versus an unknown or uncredited cal, it makes your unit measurement a little bit risky there. Last one. So system specification. So this is kind of the culmination. We zoomed in on the sensor. Really understand the fact that there's specifications for the entire system. So you're going to have your instrumentation. You're going to have potentially cable influence. You're also going to have maybe some influence from fixturing. So again, how we attach to a load cell, how we calibrate, how we can then hit those performance specifications, it's going to be a function of how we're attaching to that load cell. So always want to follow best practices, because if you want to try to get the performance that is specified on a data sheet, you got to make sure you're hooking up to the load cell correctly and that you're utilizing it in the proper manner there. We talked about it before, not all specifications will apply, but through best practice and also understanding from an application standpoint, you can really eliminate most of the specifications on a data sheet, and you're going to be left with 3 or 4 maybe that are of importance when you're looking to select a sensor for testing.